Okay, so welcome to the next section, section 5.3. This section is titled the Fundamental Theorem of Calculus. Named after the theorem we're going to be spending all section talking about. Now, with a name like a fundamental theorem, you know that this theorem is going to be a pretty big deal. So, but we need to work up to talking about it. So, I'm going to start with a question. So back in the end of chapter 2, we had the limit definition of the derivative. And we said this is a number. Can we take this derivative at a point and make it into a function? The answer was yes. The idea being that if I gave you, the idea was that I had this thing calculated ahead of time, so you give me an x, I give you what the derivative at that point is. So we could start to think, can we do a similar thing for the integral? Usually we have from a to b f of x dx. This is a number. Now, and I'm going to change, just for the time being, I'm going to change this. Instead of writing it in terms of x, I'll write it in terms of t. So this t is sort of functioning similar to how this delta x is. It's something that there's a limit going on in there, but is not what you're varying. Is not your variable. Right now, this is a number. It's not a function. So we want to think, is there a way I could change this integral to make it into a function? And we can. Let's just make one of the limits of integration x. So if you give me a number that I will then plug in to the top part, is this a function? And well, yes it is. For every x value, you get a number back. It's an area, so it's a function. What type of function is it? Is it continuous? Is it differentiable? Those are questions we've asked before. A lot of our functions are differentiable no matter where you go. They're differentiable everywhere. Other functions are differentiable at most places. You think of piecewise functions and the absolute value function. Absolute value is continuous everywhere, but not differentiable at 0, versus a piecewise function that's both not continuous and not differentiable everywhere. So this is a valid question to ask. It's not something we get for free just by saying, well, this is a function, so of course it is. Now, looking at this function, if I call this, let's call this right now capital F of x. If I look at capital F, you could compute it during certain times, like if I make this graph, very specific functions we might be able to compute using that whole fact that the integral is the net change. For example, here, if you did f of 2, that would be taking my a to be 0. That's from 0 to 2. And then this function, f of t dt, where this is my function f, well, that's just this triangle half, and then base times height, which is 1, versus f of, say, 3 is from 0 to 3 f of t dt, or the positive area that we already calculated minus the negative area, or 1/2. So there is ways of constructing this function and working with it and it making sense in the terms of it being a function. Now we get to what the name of the section is, the Fundamental Theorem of Calculus. So, the answer to that question about continuous and differentiable is yes. But not only yes, it tells you what the derivative is. So let me write down the Fundamental Theorem of Calculus, Part 1. We'll talk about Part 2 in the next video. So Part 1 says that if you have a continuous function on some interval, then, and you take this function, I'll call it g of x here, from a to x, f of t dt, that this is continuous on that closed AB and differentiable, well, because we don't know that it's defined for x values less than a or x values greater than b, all we could hope for is on open AB. Further, the derivative of g is f of x. So not only does it tell you that it's continuous and differentiable, but the Fundamental Theorem of Calculus tells you what its derivative is. Now this will be, I will often denote it as Fundamental Theorem of Calculus, and then 1. Just to denote it from Part 2 that we'll be talking about tomorrow. Okay, so what is an example of how we could use this? Well, if we take g of s to be 5 to s t minus t squared to the 8th power dt, then g prime of s, all we do is we look at the function, this function, and anywhere where we see a t, we plug in an s. And that's it. That gives us the derivative. No other work required. So let's do some more examples of that. So, a little quick thing about working with this part, and I'll write it up here, is that it can be written as the derivative with respect to x from some number to x, f of t dt, equals f of x. Okay, so let's let g of x be 1 to x natural log 1 plus t squared dt. Okay, what's its derivative? Well, that's just going to be the derivative of this thing, which, based off Fundamental Theorem of Calculus, part 1, is natural log 1 plus x squared. So, that follows. Quick enough. Okay. Now, what about an example where it doesn't quite look like that? Like, say, from x to 0 of square root 1 plus secant t dt. So before I had the number on the bottom limit of integration and variable on the top. But now I have the variable on the bottom, number on the top. So that's not going to work if we want to calculate f prime. But we have a nice little rule, remember, that says if I put a negative sign out front, I can flip them. Oh, and look, now it looks the way I want. So f prime of x, you keep the negative sign, but then you do square root of, replace every x, every t in the function with x. 1 plus secant x. And that's how this works. Okay, just one last example. Oops, I didn't mean to erase that. T dt, and you take a derivative with respect to x equals f of x. Okay. Now here's a more challenging example. First, notice that I have them flipped like I did in the last problem. Numbers on top. But also, the other problem I have is I have a sign x instead of just x. That is going to be a problem. So, what do we do about it? Well, we could use the chain rule. Right? Because if we want to find y prime or dy dx, the chain rule says that this is dy d sine x times d sine x over dx. Or in other words, what this tells us is that what we could do is this change of variables. And then, so y is from u to 1, square root of 1 plus t squared dt. Introduce the negative sign to flip them. So if we want to find y prime with respect to x, this will be dy du times du dx, and du dx is cosine x. Okay. So, what is this y prime, this dy dx equal to? Well, it's the derivative of this thing with respect to u, which we know now by the Fundamental Theorem of Calculus, part 1, is going to be negative, remember the negative sign out front, square root of 1 plus u squared. And then you have to multiply that by, chain rule says, dy dx, which is, or du dx, which is cosine x. And to get our final answer, all we have to do is plug in, well, what is u? And u is going to be sine, so it's 1 plus sine squared x. And there we go. That is what the derivative of that function is. Now, I went through the long way. The short way of thinking about this problem that they'll mention in one of the supplemental videos I posted on Canvas is that you can think about this as first, well, you have to flip them, but then to take the derivative, it's going to be negative square root of 1 plus, plug in that there. But then you always have to multiply by whatever the derivative of this is. So you could just do it in one step if you want. I was just trying to go through and explain why I was doing what I was doing. So if you have any questions, just send me a message or comment. And I will see you all tomorrow for Fundamental Theorem of Calculus Part 2.